And as I told already some of you in a different occasion, one thing I forgot to mention is that all these features of Office 2010 do not quite work if you are over 30. So I apologize if something would look clumsy, but still there are definitely some things that you can do here that maybe you can't do on the blackboard. And please don't hesitate to ask me questions or to stop me, make comments whenever something doesn't make sense or whenever you feel like, or whenever it does make too much sense. So left, let me see. Okay, so I'll be talking about weak and strong and weak epsilon nets and their applications, and hopefully this will make more sense soon. So let me start with some definitions. I'll just try to tell you what these things mean. And here are these definitions. So the first thing I defined is what is called a range space or a hypergraph. So a range space is a pair, ordered pair, X and script F that you see there, where X is a finite or infinite set of objects or points, we'll call them, and F is just a family of subsets. So this is a range space, or you can call it a hypergraph. This is more the combinatorial terminology. I have to find some way to waste time without saying too much, because it seems people are still coming. But let me see how I manage to do that. So when we have such a range space, we say that a set A of points in this range space is shattered if it can be separated in all possible ways by intersecting it with a range in your family. Namely, formally, for every subset B of A, there is some range, this F in our family of ranges, so that if we intersect it with A, we get exactly B. Right? So if A is finite, then we have all the 2 to the A subsets that we can obtain them as intersections. And then we want to define the VC dimension, or the Vapnik-Chervonenkis dimension of this range space. So this will be the supremum cardinality of a subset of this range space, which is shattered, which can be separated in all ways. So this can be finite, and actually the interesting cases will be when it's finite, but formally it can be infinite as well when there are shattered sets of all finite sizes, or when there is an infinite shattered set. Okay, but in the interesting examples, this will be finite. So let me see some example. So suppose the objects or the points are just all the points in the plane, and the ranges are all the half planes, which means that we take a line and we take all the points above or below the line. Okay? So the claim is that the VC dimension of this is 3. That's not difficult to see. So you see that if you have 3 points there, as you see in this picture, I just realized, okay, we'll see it. It seems to me that I don't get, that shows me always all the picture together, and I don't get separately, right. But we'll see if there will be anything bad with this. But yeah, anyway, but yeah, and it seems to me that this connection changed the VC dimension from 4 to 3. Anyway, so if you have these 3 points here, then obviously there is a half plane containing all 3 of them. There is a half plane containing any one that we want. There is a half plane containing any 2, and there is a half plane not containing any one. And it's not difficult to check that if we have 4 points, then we cannot separate them in all possible ways, because if, for example, they are in convex position, then we cannot separate these 2 from these 2. And if they are a triangle, the convex hull is a triangle, and there is 1 point in between, then any half space that will contain these 3 points will also contain the 1 in the middle. So the VC dimension is less than 4, it's at least 3, and therefore it is 3. Here is an even simpler example, and that's the points are all the points in the plane again, and the ranges are lines. Okay? So here the VC dimension is 2. If you have 2 points in the plane, then there is a line containing both. There is a line containing any one of them. There is a line not containing any. And of course, if you have 3, if they are all on a line, then you cannot contain 2 of them without containing the third by line. And if they are not on a line, then you cannot have all 3 of them. Now here are some more examples. So if x is now so that's just the obvious generalization of what I said before. The points are all the points in the d-dimensional Euclidean space, and again the ranges are all the half spaces. We take a hyperplane and all the points in one side of it. Then the VC dimension is d plus 1. If we take d plus 1 affinely independent points, so say 0 and all the unit vectors, then we can separate them in all possible ways. And if we have d plus 2, then there is a simple theorem of Radon tells us that if we have d plus 2 points in Rd, then you can always separate them to 2 disjoint sets so that the convex hulls intersect. That's a simple linear algebra exercise. And if these 2 sets, the convex hull, intersect, then you will not be able to separate one set from another by a hyperplane because the convex hulls intersect. So the VC dimension is less than d plus 2. It's at least d plus 1. So it is d plus 1. A more general, slightly more complicated example is, again, the points are the points in d-dimensional space. And we take all the semi-algebraic sets of constant description complexity S. So that means that we are allowed to have some constantly many polynomials of constant degree, polynomial equalities and inequalities. We take the intersection of everything. That will be a typical range in our set. And then you can use some simple results from real algebraic geometry of Milnor or Warren and show that, again, this VC dimension is bounded by some function of the number of polynomials, the degree of polynomials, the number of variables. So if you want, for example, if you take balls in R17, so that's an example, right? Because we can write it by some polynomial inequality. Or if you take balls, the intersection of balls with half planes, it's also a semi-algebraic sets. So each of those examples will have finite VC dimension. Okay. Now, okay, we'll soon see what happens now. But, all right. So here is in the title I was talking about strong and weak epsilon net. So let me define what these notions mean. So this is the definition of strong epsilon net. Sometimes it's just called epsilon net. So we'll have, again, some range space. And inside it, we have a subset that I denoted it here by A. And now this subset is finite. Right? So this A is a finite set. And we'll call a subset X of A an epsilon net if it somehow represents all the big ranges. Namely, whenever I have a range F that contains at least an epsilon fraction of the number of points in A, then it must contain at least one point from this epsilon net X. Okay? So here is an example. Epsilon, we have here a set of 8 points. And epsilon is 3 over 8. So, and let's say that the ranges are half planes. So whenever I have a half plane that contains at least 3 points, I want to contain something from the epsilon net. And here is the epsilon net. So it still works. So these are these 3 points. And indeed, if you take any half plane, that's one example, all the points to the right of this line, then it must contain one of these big points, one of the epsilon net. Okay, so this is the definition of an epsilon net. And there is a related notion, and I just mentioned it, and this is called epsilon approximation. So now we want not only to capture the big sets, but we want to approximate the size of every set kind of faithfully. So again, we have a finite set of points A in this range space, and we call a subset of it X an epsilon approximation if whenever we take a range and we look which fraction of points of A this range contains, it should be about the same as the fraction of points of the epsilon approximation, namely of X, that the range contains. So the difference between these two is less than epsilon. And you see that if something is an epsilon approximation, it's obviously also an epsilon net, right? Because if this thing is bigger than epsilon, then this thing cannot be 0, otherwise the difference would be too big. And it's easy to see that the converse is not true in general, so somehow an approximation is a stronger notion. Now, what is good about these things? So here is a theorem that's a result by Hausler and Welzel, proved in the late 80s. It's actually very similar to the original proof of Vapnik and Chervonenkis that I'll mention in a minute. And this says the following, that if we have a range space with finite VC dimension, so denoted by D, then any finite set in it contains a small epsilon net. And how small? The size of this epsilon net is at most some constant, maybe 10, times D over epsilon, log of 1 over epsilon. So think about D as constant, epsilon is very small. So one thing to note here is that this size is independent of the size of the set, of the big set A. Right? So for example, it would mean that if you have a huge set, many points in the plane, millions and millions of points in the plane, and let the range space be, I don't know, all the triangles in the plane, so it's easy to see that this also has some finite VC dimension, maybe 7 or 8. Then what this says is that from this huge set of points, we can find some 1,000, let's say, independent of how huge this set is, so that any triangle that contains at least 10% of the points contains at least one of my 1,000 points. Okay? And the proof of this is, so actually, I wrote here something about this. Yeah, so two things to note is that indeed the size of n is independent of that of A. And let me also mention, before I say something about the proof of this, is that if the VC dimension, so this means that if the VC dimension is bounded, is finite for some range space, then always there are very small epsilon nets. Very small means that even if the set A is very big, then there is always epsilon net whose size is independent of the size of A, and in fact is almost linear in 1 over epsilon. Now, on the other hand, there is some sort of dichotomy here, because if the VC dimension is infinite, so there are shattered sets of all cardinalities, then there are some sets, namely a shattered set. So if for your A here, you will take a shattered set, and you want now to have an epsilon net for this set, then you have to take almost all the set, right? Because you cannot even miss an epsilon fraction of it, because otherwise there is some range, that was the definition of shattered, there is some range that intersects it by exactly this epsilon fraction. And if we didn't take any point for this epsilon fraction, then we missed completely this range, although it contains a big fraction of the set. So it means that if the VC dimension is unbounded, then for some sets A, we have to take almost all the set in order to have an epsilon net. If the VC dimension is bounded, then we have to take, or it's enough to take a very small subset to have an epsilon net. And the proof actually shows that it's enough to take a random set. So if you take a random set of size, I don't know, 10 times d over epsilon, log of 1 over epsilon, then with high probability, this will be an epsilon net. It's kind of, it's an elementary probabilistic proof, but a very clever one, because somehow if you do the more or less obvious thing, then there will be a logarithmic dependence on the size of A. And somehow you need some clever argument to to get it independent of the size of A. Now, actually, as I said, this is similar to the proof of Vapnik and Chervonenkis, and they proved more or less the same result for epsilon approximation. There's the estimate you get is a little different, but again, it's independent of the size of the set. If you have a big finite set in a range space of bounded VC dimension, then it always has an epsilon approximation of size at most constant d over epsilon square log of 1 over epsilon. So again, just a function of the VC dimension and of epsilon. And again, actually, a random set with high probability will have this property. So these things are useful, and I wrote here that, and I'll just describe one example, but that these epsilon nets and epsilon approximations, they have a lot of applications in discrete and computational geometry, in computational learning, in combinatorics, in probability, in other areas as well. And let's just see one example. So that's a very naive example, but I think it explains why something like that could be useful. So, so I'm saying that the existence of these small epsilon approximations implies the following. Suppose, again, you give me this huge set of points in the plane. So I have some points in the plane. And now what I want is to store some information, maybe not so much information, that will enable me to approximate the number of points inside any given triangle. Because you will come to me afterwards, and you will ask me, here is this triangle, these are the coordinates of its vertices, how many points it contains, and I'll have to answer it approximately. So I say that what I can do is just to take an epsilon approximation of this set. So these are constantly many points, just some function of epsilon, right? This is because the VC dimension for the range space of triangles is bounded. And now when you give me a triangle, then I just check how many of these 1,000 points, let's say, that I stored, how many of them are contained in this triangle. And if there are 300 among the 1,000 of them, then I will approximate that this triangle contains 30% of the zillions of points that I had. And if this is indeed an epsilon approximation for epsilon equals 1%, I don't know, then this will give me a good estimate up to 1%, right? So this says that we have.
In practice, you would actually construct this probably not. Your proof's probabilistic.
Yeah, the proof is probabilistic, and you will construct it probabilistically, indeed.
Do you know when you have a good thing?
No, yeah, this is right. So I mean, the proof can be de-randomized. Namely, I could find this explicitly, and then I will know. But then the trouble is that the running time of this depends on the big set, of course, right? Because I have. So it means that in time which is nearly linear, or let's say in the size, or definitely polynomial in the size of the input, I can check that this is indeed the case. But normally I'll not bother, right? Because I don't want. There are all these billions of points. I'll just choose randomly a small number of them, and then I want to forget the other points. And now, because of this probabilistic proof, I can make sure that with the probability of failure, so this will be an epsilon approximation with probability 99.99%. Okay. But, all right, so this is, as I said, a kind of naive applications. There are more sophisticated ones, but I think it shows why this can be indeed useful. All right, now as we said, there was this estimate of d over epsilon times log of 1 over epsilon, and we want to know how tight it is, and there was an early example by Komloch, Spach, and Wogiger. There are some other examples as well, that at least in the abstract setting, there are some abstract examples of range spaces of VC dimension 2. Now, in VC dimension 1, things are very simple. It's kind of understood how these spaces look, and there are no surprises, let's say. But in dimension 2, already there are examples where indeed the smallest epsilon net for some sets are of size, some constant 1 over epsilon, log of 1 over epsilon, namely this log is required. And somehow this log, so I'll talk quite a bit about this log, somehow people care about this log. I'll mention later why they are important, but let's say that we want to know if this log has to be there or not. And specifically, this was a problem suggested by Matuszek, Seidel, and Welzel some 20 years ago. And they asked, so as we said, in the abstract setting, we can construct these spaces with VC dimension 2, which require big epsilon nets. But somehow the thought was that maybe in all the natural geometric settings, like the examples that I show you, if the VC dimension is small, then maybe the logarithmic factor is not needed, and the size of epsilon net could be always linear in 1 over epsilon. And actually, there was some evidence, quite a bit of evidence over the years that this could be true. So I wrote here a few examples. So this is the case for points and half spaces in 2 and 3 dimensions, and then for points and disks or pseudo disks in the plane, whatever this means. And then for some dual configurations, and let me not define what dual configurations mean, but again, it's some natural geometric scenarios. And I listed here some sequence of papers that deal with special cases where indeed you get results that are linear in 1 over epsilon. And each of them so they use different techniques, and they are often quite sophisticated and interesting. So it looks that every example needs some new idea. And still, as most of these papers write in the concluding remarks section, the prevailing conjecture has always been that indeed in all the geometric scenarios, there are always epsilon nets of size linear in 1 over epsilon if d is constant. And as I said, this is somehow, so it may look that the log is not so important. What is the log 1 over epsilon term between friends? But actually, this appears in some algorithmic questions. So for example, if we look at geometric instances of set covers, so think about the following example. Let's stick with the triangles example that I have. So I give you in the plane a family of triangles. Now there are no points here. There are just triangles. So you look at some set of triangles in the plane, and you have to find a minimum number of points in the plane that intersect all the triangles, that capture all the triangles. So you want to solve this problem. This is an instance of a set cover problem. It's a hard problem. You want to approximate it. So you can solve this question fractionally. So this means that you can choose fractions of points, and so that inside each triangle, the total fraction you have is at least 1. This you can solve exactly, efficiently by linear programming. And then you want to round it, or to know what is the difference between the integral, the ratio between the integral solution and the fractional solution. And this is exactly this log 1 over epsilon term. So this is really like the 1 over epsilon appears already in the fractional solution. And if indeed the ratio, if there are epsilon nets of size linear in 1 over epsilon, then this fractional solution will give a constant approximation to the integer solution. Otherwise, there will be a factor of this log of 1 over epsilon. OK, so we want to know about this log. And one thing that I'll try to show you, quite new, is that indeed this is false. So there are examples where we do need more than linear. And in fact, there are very, very natural geometric examples, more or less the simplest natural example you can think about, just points and lines in the plane. Okay, so the example is points in the plane will be the the points or the objects, and then the ranges will just be lines in the plane. And the claim is, unfortunately, it's a very weak nonlinear bound. So for some configurations of points in the plane, with respect to lines, you will have to choose an epsilon net of size constant 1 over epsilon times inverse Ackermann of 1 over epsilon. So that's a function that goes to infinity when 1 over epsilon goes to infinity, or when epsilon goes to 0, but it goes very, very slowly to infinity. Yeah.
Is that the same true if you allow the epsilon net points outside the set X?
Yes, so this will be weak epsilon net, and I'll come to this in a minute. And the bound still holds in this example, but so it's a good question, but let me come to it later. Again, something, all right. And even newer subsequent, okay, and there are some similar results for others, but let's not worry about that. Here's a newer subsequent result by Pach and Tardosh. So it says it's for some other geometric scenarios. For example, if you have axis parallel rectangles, so again, you have points in the plane and axis parallel rectangles, then sometimes you need a bigger bound. So you need 1 over epsilon times log of 1 over epsilon, which log may look small, but it's much, much bigger than inverse Ackermann of 1 over epsilon. And there is a dual planar example, which is kind of more complicated to describe, so let me not describe it, in which you really need 1 over epsilon times log of 1 over epsilon. Okay? So really, we need these extra terms. And I should say, and this is related to what Shahar was asking, that the first example, so the second one maybe does not, or we don't know, but the first example works for what is called weak epsilon net as well, namely when we are allowed to choose points outside the original set. And that gives me an opportunity to talk a bit about weak epsilon nets, which I think are also, I'll try to convince you that they are also interesting. So let me tell you what we mean by these. So it's kind of easier to have a weak epsilon net. We have more freedom. So we have, again, a finite set of points in a range space. So we have some range space. We have a finite set of points. And we'll call a set Y of points a weak epsilon net for A, again, with respect to the ranges, if exactly the same condition that held before for the strong epsilon net holds now for Y, namely, whenever we have a range that contains at least an epsilon fraction of the points of A, then it contains at least one point of this Y as well. All right? But why is it weak? Because now we don't force Y to be a subset of A. It can be some other points of the range space. Okay? We'll see that sometimes this is useful, so I think I wrote it here. Right? So Y is not necessarily a subset of A. And therefore, there may be small weak nets for A even when there are no strong nets. And I'll tell you some examples where this happens. So it's easier to get weak epsilon nets, and therefore it's harder to prove lower bound for them. Right? We have more flexibility. And still, we'll see, as I wrote here, that even those are not necessarily linear. And let me say something about weak epsilon nets. So let's talk about weak epsilon nets for convex sets in general. So what is written here? We have a set of endpoints in RD. In the picture, they are in the plane. In the plane, actually, it's interesting enough. And we have some parameter epsilon. And now what I want is that for every convex set that contains at least an epsilon fraction of the points, then it will contain at least one point of my weak net. Right? So let's see how this goes. So the objective is to construct a point set Y that stabs all the convex hulls of at least epsilon n points of A. Whenever we take epsilon n points, we take the convex hull. Then it should contain some point of Y. And there should be here some. So here are the points of Y. There are these blue pluses. and let epsilon n be 4. So whenever I take the convex hull of 4 points, like this one, or this one, or this one, or this one, you see they always contain one of the blue. You want to see it again? Yeah. All right. So they always contain some of the blue points. And you see that indeed the blue points are not part of the black points. And of course, in general, it is hopeless to, because we could have chosen all the black points to lie on a circle, let's say, to lie in convex position. Now, on a circle, the convex hull of any subset of the circle does not contain any additional points of the circle. It contains only these points. Namely, all the points of the circle are really shattered in the range space consisting of all convex sets in the plane. So the VC dimension is infinite. There is no hope here to get a small, strong epsilon net. We would have to take essentially all the cycle. But a weak epsilon net we can. And in fact, this is true. And this is something that we, in some ancient result with Baran, Furedi, and Kleitman, is that any finite set of points in the plane admits a weak epsilon net of size constant 7, let's say, over epsilon square with respect to the family of all convex sets. Here, this epsilon square is not necessarily tight. And there are some analogous results for higher dimension as well. So whenever you give me a big set of points in the plane, and you give me some epsilon, I can choose some 7 over epsilon square points in the plane. Other points are not part of these points, not necessarily. And whenever a convex set contains an epsilon fraction of the points we started with, then it contains one of the new points that I'll choose. Why is this useful? So again, weak nets appear quite a lot, maybe not so much as maybe not so much as strong nets, but they appear. And I'll just tell you something about one application, one combinatorial application, or an application in combinatorial geometry. So that was a problem of Hadwiger-Debrunner raised in the 50s. They called it the PQ problem. It's an extension of Hales' theorem, as I'll soon explain. And this is something we proved with Kleitman. So it says the following. So suppose you give me two numbers, P and Q. Let's talk about the plane again. We can talk here about any dimension, but the plane is good enough. So give me two numbers, P and Q, and suppose P is at least Q and Q is at least 3. Otherwise, this thing will not be true. And then you have a collection of planar convex sets, so that whenever you have P of them, then among these P you can find Q that have a common intersection. Okay, so that says that they satisfy the PQ property. And then the claim is that we will be able to find some small number of points in the plane, some function of P and Q only, which is independent of the size of the family and the description of the family, so that they will pierce all the sets in the family. Every set in the family will contain at least one of these points. So here I wrote some, you see some trivial example, but I'll soon mention a more interesting one. So you see that this example has, let's say, the 4-3 property. What I mean by this example is that we have this set here, and then we have very, very many other sets, and they all contain 1 point. So it's not such an interesting example, but still to practice the definition. So whenever you give me some 4 sets in this family, then at least 3 of them will come from the right side, and then they all have a common point. And then the theorem will say that with some number of points, well, here with 2 points, we just choose 1 point here and 1 point that is common to all those, we can intersect all these sets. Okay, and this is true always. So let me just mention that this is an extension of Hales' theorem. So Hales' theorem is one of the very basic results in convexity, proved almost 100 years ago, although it took him some time to publish it. And his theorem really says that if you have a family of compact convex sets in the plane, and among, well, let's say at least 3 of them, and among any three, some three, namely these three, have a common intersection, so every three have a common intersection, then all have a common intersection. You see a picture here, I'm not sure how good it is. So we have here like 4 sets, and each 3 have a common intersection, and because of this, all 4 have a common intersection. So Hales' theorem says that if every 3 sets in the plane, or in dimension d, every d plus 1 intersect, then they all intersect, and Hadwiger-Debrunner is some sort of an extension. If among every 10 you have some 3 that intersect, then you can capture all sets by 100 points, something like this. And why is this relevant to a weak epsilon net? So I think it's a very simple to understand. So think about the following example. So this is, again, an example of a family of convex sets that satisfies the PQ property. So what is this example? So put in the plane very many points again, so n points. We can think about a continuous probability measure as well, but it will be better to think about discrete measure. So let's think about n points in the plane. And look at your family of convex sets will be the family of all convex sets that contain more than q minus 1 times n over p of the points. That contains quite a bit of the points. Right? Now you see that if you take p of these convex sets, then altogether the sum of the number of points that they contain is more than q minus 1 n over p times p. So it is more than q minus 1 times n, which means that one point is covered q times by at least q of them. Right? So just the total measure of p points is too big, and therefore some point belongs to all of them, to q of them. So this means that whenever we have p sets, then some q have a common intersection. All right? So if we want to prove this Hadwiger-Debrunner for this example, we have to show that for this example, we can find some small number of points that intersect all these convex halves. But this exactly means a weak q minus 1 over p net for convex sets, right? Because exactly we want that inside every convex set that contains at least q minus 1 over p times n of the points, then we'll have one of our points. Okay? And somehow, so this is an example where indeed you see that what you need is exactly this weak epsilon net. And somehow the main part of the proof is to show that the general case can essentially be reduced to this. And that uses something called fractional Hales theorem, which is a result of Kachalsky and Liu, and really a linear programming duality, or the minimax theorem of von Neumann. Now you see that this is, so when you prepare PowerPoint presentations and you want a picture, then you go to Google Images and you write the minimax theorem. This is what I did here. Then you get this picture. So it's not completely clear why this is a minimax theorem, but I think it's a nice picture, so it is here. All right. So a little bit more about this weak nets. So I already told you that any finite set of points in the plane admits a weak epsilon net of size 7 over epsilon square, or constant over epsilon square, with respect to the family of all convex sets. And actually, if the points are in a convex position, so this is something more recent with Kaplan, Niva, Sharir, and Smolensky, that if the points are in convex position, then actually there is a weak epsilon net of size 1 over epsilon times, again, this inverse Ackermann of 1 over epsilon. So something that is almost linear, but not quite linear. Well, we knew it only as an upper bound, but actually this turned out to be tight. So this is a slightly more recent result by Buch, Matuszek, and Nivash. And what it says is that some planar sets require weak nets of size 1 over epsilon log of 1 over epsilon. Remember, the upper bound was this constant over epsilon square. And some planar sets in convex position require nets of size 1 over epsilon times inverse Ackermann of 1 over epsilon. So this result with the inverse Ackermann is really tight, which shows that indeed inverse Ackermann appears naturally in some of these problems. I mean, of course, not all these inverse Ackermanns are exactly the same inverse Ackermanns. So Yeah, so it's good to think about it as a function that grows to infinity very slowly. I can tell you quickly the definition. So you define the Ackermann function recursively. It's a function of two variables, a, I, j. So a 1j is defined as 2 to the j, and a ij is defined as ai minus 1, comma aij minus 1. So it's something that grows. This is the Ackermann hierarchy. So the first one will grow like powers. The second one will be like the tower, 2 to the 2 to the 2 to the 2. The third one is iterated tower. It's sometimes called the wow function, and so on. And then the Ackermann function is a diagonal of this, aii. And the inverse, so it's big. And the inverse of this is the inverse of this. So it is small, but it grows, right?
Is that the any definition? I mean, so since you say it's...
Yeah, because so the version usually depends if you start with 2 to the j or with the Ackermann function, but they are all so big or so small that it's essentially the same. So up to a constant, I mean, this inverse Ackermann function is never more than 3 for the number of atoms in the universe, right? So if we allow a multiplicative factor of 3, then, but yeah, but it grows, yeah, it somehow appears.
Is this common to have an upper and lower bound which are both involving other games?
Right, yeah, so there are several known examples. There are probably the union found is probably the first one, and then in geometry there is something called the Davenport-Schinzel sequences that you will like because it comes from Davenport, basically, and Schinzel. And so it's a combinatorially defined. And then there are several things, several examples in geometry. So somehow it appears. Right. So good. And what I wanted to say here is that these are all bounds with respect to all planar convex sets. But actually, the new example I told you tells us that some planar sets of points require weak epsilon nets of size this 1 over epsilon times inverse Ackermann, even just with respect to lines or triangles. So we don't need all convex sets. It's enough to take some very restricted family of convex sets, and still we need this inverse Ackermann. Okay, so it is common to say that a lecture should contain one proof and one joke, and it's better if they are not the same. Here they will be almost the same, because so I want to show you indeed one proof. One proof here is really extremely simple. So so this will be the proof for the existence of examples of points that with respect to lines require strong nets which need this inverse Ackermann. So this I want to more or less describe. The weak nets is a little bit more complicated, so I won't do that, but let me just try to describe that. So it's really a very simple proof, even if we just have to do it in the next 10 minutes. So it's a proof that really you can understand in the last 10 minutes of lecture. But it applies something pretty deep, and that's the density Hales-Jewett result, which I'll tell you about. And here, actually, I have another one of these pictures. So if in Google Images you write Hales-Jewett theorem, this is the picture you get. And actually, there I went to see what this is about. And it's in a blog of someone. He's writing about something. And he actually writes that this picture has nothing to do with the Hales-Jewett theorem. However, he writes, the Hales-Jewett theorem does not lend itself to any interesting pictures. And I wanted to put here some pictures, so I put here this one. So I follow him and do the same. All right, so let me tell you what this density Hales-Jewett theorem is, because that's a nice statement. So that's unrelated to, I mean, that's independent of what I said so far. So even if you lost me, I mean, you can listen to this again. That's an interesting statement to know. So we have to define what is a combinatorial line. So that's just a set of points of vectors of length d, whose coordinates are integers from 1 up to k. So we look at vectors, very long vectors, because d will be very long. So vectors of length d, and each coordinate is an integer, 1, 2, 3, up to k. And what is a combinatorial line? It's a set of k points. In some coordinates, all of them are constant, and in the other coordinates, they progress. So the first point has 1 in all these coordinates, the second has 2, the third has 3, and so on. So you see here an example. Here k is 3, d is 7. You see that all these 3 vectors are constant in coordinates number 2 and number 5. And in the other coordinates, 1, 3, 4, 6, and 7, the first point has 1, then the second vector has 2s, and the third has 3s. So this is a note that if you think about these points as points lying in the Euclidean space, this is also a line. These are points on a line, right? The direction of this line is just the vector, well, it's obvious vector.
The
Okay.
red numbers doesn't have to be the same, right, along the coordinates?
No, they don't, right? So you mean the fixed coordinates? Yeah. So in the example, they are not the same,
No,
right?
the red ones, not fixed. It doesn't
No,
have
the
to be
red
one.
ones, it's important that in the first point, they are all 1.
Yeah.
In the second, they are all 2. In the third, they are all 3. Yeah, yeah, they are the same. So this is right. Okay. So this is a combinatorial line. There are quite many of them if the dimension is big. And this density Hales-Jewett theorem, so this is a result of Fürstenberg, Katzenelson, they first proved it for k equals 3. So for k equals 2, it's pretty easy. It follows from Sperner's theorem, a basic result in extremal finite set theory. For k equals 3, it's already pretty difficult. And for a general k, it's a bit more difficult. This is an extension of Semered's theorem about arithmetic progressions. So it implies Semered's theorem immediately. And also with Semered's theorem for k equals 3, it's not so difficult. So this is Roth's theorem. And for general k, it's a bit more difficult. So, or it's more difficult. And all right, so this one is something a bit stronger. So what it says is the following, that we fix a small delta. But for us, actually, delta equals half will be enough. So think about, we fix the small delta. Then if the dimension is big enough, then if we have a set of at least delta times k to the d points in kd, so a delta fraction of all these vectors, then it contains a combinatorial line. It's hard to avoid this combinatorial line. Every set of 1% of these points will have a combinatorial line if the dimension is big enough. Big enough is pretty big, but and you see that this is, in fact, almost what we want, because this means that think about the range space whose points are the vectors in this k to the d. So these are just, think now about them as points in the d-dimensional Euclidean space. And the coordinates are integers between 1 and k. The dimension is d. And the combinatorial lines are lines, right? So they are some of the lines. So if my epsilon is very small, it is k over k to the d, then if I want to choose a strong epsilon net for the lines here, I have to choose at least one line in at least one point in every combinatorial line, right? But for this, I have to choose at least 1 minus delta fraction of all points, because if I avoid delta fraction, then this delta fraction will actually contain a combinatorial line. So it means that here, every strong epsilon net is actually big. It is somewhat bigger than, it exceeds 1 over epsilon by a factor of about k, of nearly k, right? Because 1 over epsilon will be k to the d divided by k. The only trouble with this is that this is not, we wanted an example in the plane, in very low dimension, right? And this is an example in very high dimension, really very high, because somehow d has to be very big for this theorem to hold. But this is not really a problem, because we can just project it on the plane. So really, what we do is we just take this example, and we project it randomly on 2 dimensions. If the projection is generic, is random, then with probability 1, well, of course, every combinatorial line is mapped into a line. And with probability 1, you will not have on this line any other point besides the points that were supposed to be there, that belong to this combinatorial line. So if you have to hit this line by some epsilon net, you have to choose one of the original points that were on it. And as we said, this set will be big. Okay. So basically, this is it for a strong epsilon net. As I said, for weak, you have to work a bit more. Let me just say, so I still have a bit more than 5 minutes. So let me just say that the original proof of first-magnetic Katzenelson is ergodic theoretic, and therefore it's non-effective. So it doesn't give us really any bound, even not this this inverse Ackermann. Yeah, it doesn't. Okay, it does not give. I mean, yeah, it uses compactness in a, so it doesn't give any estimate. Okay, so by effective I mean constructive, or so it doesn't give any estimate. I wouldn't be able to write their inverse Ackermann if there would have been only this proof. But somehow there is a subsequent proof, and that's a more recent one obtained by, that's actually the first and most successful polymath project that probably all of you or almost all of you heard about this polymath, but let me say something about it anyway. So this gives an effective bound. So this polymath project was an attempt initiated by Tim Gowers. So he wanted to see how, and I apologize for those who know about it, so how effective it can be to have some massive collaboration over the internet working on mathematical problems that without meeting before. So you want to allow everybody in the, not in the universe, but on Earth, let's say, to help you in this. So the idea is to post this, to choose a problem, to post it on some sort of wiki page or blog where everybody is allowed to post comments. So there are some rules on how this is done, and everybody can contribute. Now, of course, and the hope is that this will convert to something intelligent. Now, of course, you could have guessed, or my guess would have been, if I would have been asked about it before I saw it, that most of this would be nonsense, right? Everybody is allowed to write a comment. So you expect that most comment would be, I don't understand what is a line. Can you explain what I'm, because it's everybody. But still, so the first problem that they took was this density Hales-Jewett theorem, and the objective was to try to find an elementary effective or constructive proof that would give a bound for k equals 3. This was in January 2009, and in less than 2 months, so in March 2009, they basically solved it, not only for k equals 3, because the proof actually extended for general k and gave actually this effective bound. So quite a lot of people posted comments. The slightly disappointing thing maybe is that the number of people that eventually contributed is not much bigger than the number of people in a typical paper with many authors, so maybe 6 or 7. And maybe another so far disappointing thing is that since then they tried at least 10, maybe 15, depends how you count, more questions of this type. And so far, none of them has been successful. I mean, there were some very partial results on some of them, but so far there hasn't been anything about. But still, somehow, I think it's very interesting as a kind of a new way of working on mathematical problems. And in fact, last year we had some discussion about this. But
do you actually use this in some of your?
Yeah. So I use the if I want, because I wanted to write inverse Ackermann, so I use this, and there is no other. This was the first proof that gave an explicit bound. Right? So you could say that this polymath. But I think it's very, and the proof there is more elementary, so kind of it's an interesting proof. So as I said, the proof for weakness, you need to work somewhat more. Let me not talk about this. I want to finish with, so I'll mention 2 problems, but let me also tell you 2 semi-philosophical remarks. Well, not very deep philosophy, but anyway. So the first one, I've seen it more than once, and I think it's good to remember it, probably most of you know it, is that when you have some conjecture and it is proved for many special cases, and you see that the proofs for special cases become more and more complicated as cases begin to be more general, then we should consider also the possibility that the conjecture may be false. So this is not always the case. There are counterexamples to that as well, but this is definitely sometimes the case. And the other comment is also not very deep, but so it just says that deep results, that's almost a definition of deep results, like this density Hales-Jewett theorem, often have interesting consequences. So it's good to try to use them. I want to mention two problems, and there is some discrepancy between this watch and mine, but I'll finish in 2-3 minutes. So the first one is that I believe that this inverse Ackermann lower bound for points and lines here is just a fluke of the proof. Namely, the conjecture would be that the minimum size of epsilon nets for some finite point sets in the plane with respect to lines is really omega of 1 over epsilon log of 1 over epsilon. And I even have a candidate example. It's not the one drawn here, or maybe, I don't know. But so I'll tell you what I think should be. I don't know to prove it, but I think that this should be true. So you just start from a grid, let's say an n by n square grid. So you have n cube points. And they are along a grid. So there are all these lines now that contain 1 point from each column. You know, the horizontal line and some lines with slope. Just you take lines that contain a point from the first column and a point from the second. If the slope is not too big, it will contain a point from every line. So these are lines that contain n points. And I want, this will be somehow the lines I want to capture. Now, of course, it's very easy to capture them in the grid. You just take one column. So what I want to do now is to take a random subset of half the points of the grid. If you take randomly half the points of the grid, then each of these lines with high probability will contain still more than, let's say, 1/3 n of the points. And I want a subset of the points now that will intersect all these remaining lines. So it seems to me that the best that you can do is choose log n columns and take all what's left in these log n columns, and that would give this bound. But somehow it's not clear how to prove a lower bound for this example or for any other example. So epsilon is 1 over n square, maybe. Like I wanted n points among the n cube. It was an n by n square. Yeah, 1 over n square, right? Yeah. By the way, in all these examples, so epsilon was a function of n, but you can kind of play with them and make epsilon, if you wish, constant and n much bigger. But let me not. And maybe, so this one question, and another one that also is related to kind of an old problem. And I don't know how related this is, but suppose you take a random set of n points in the unit square. Okay, so this is more or less what you see here, maybe. And I want to have an epsilon net with respect to triangles, let's say. So this is almost like saying what is the minimum number of points you have to choose in the square so that they will intersect every triangle of area epsilon. And the question is if this is only constant over epsilon or bigger than this. It's not more than log of 1 over epsilon. And it's not known what it is. And somehow it is, I mean, you think that somehow you take this k to the d, you project it randomly. In some sense, it looks almost random. Well, not really. I mean, there will be lines, but maybe something. I don't know.
Can't you say that something like random set does not discriminate between strong and weak? Could that be true? Not in a completely general setting, but maybe in some. So definitely I don't know to prove. It would be very nice to prove such a thing. Because as I said, there was this result of Bach and Tardosh that for aligned rectangles, and actually there it works for random set of points, but they don't know to prove anything for weak epsilon nets. And it's not, but it's
All right, so with this, I'll finish, and thank you for your attention.
Thank you.